All right, welcome everyone. Slowly coming in. We'll be starting in about 2 minutes. Thank you so much for coming in early. I'm seeing some 12 attendees so far, so we'll be starting, 2 minutes from now. Perfect. Welcome everyone. We're going to be starting in about 1 minute at 10 a.m. Eastern Standard Time. We are letting everyone know now that if you have questions, the webinar chat will be closed. You please ask your questions on the Q&A box at the bottom of the Zoom screen.
One, two, three. Ladies and gentlemen, welcome. I'm John Pugh, Director of Photonic Integrated Circuits and Quantum Technologies at Optica, and this is the second of 3 Optica online industry tutorials with Quantum Computing Inc., a company headquartered in the United States, developing both hardware and software platforms that bridge the gap between classical and quantum computing. Today in our online industry tutorial, we'll hear about the incredible progress from QCI on photonic machine learning, which offers a paradigm shift by enabling analog in-flight computation using light, drastically reducing both the latency and power usage. Remember, this is a very interactive event. We have lots of people registered, so please ask your questions in the Q&A Zoom facility in the bar at the bottom of your screen, and we'll address them at the end of the presentation from Dr. Prajnesh Vijay Kumar, Quantum Technology Lead and a tutorial sponsor QCI. Prajnesh, the floor and the attention of everyone is yours to tell us about the QCI story so far and the incredible roadmap ahead. Welcome.
Thanks, John. Hello, everybody. So today's talk is going to be focused on how we use photonics for doing computing that can be used for AI. So to give a general overview of artificial neural network, there are 3 categories. One is like supervised learning, where you have various things which I'm highlighting here, where you make the machine learn explicitly, right? And then the data will have a very clearly defined output. And the goal here is to predict the outcome or the classification or even prediction in terms of future. And you basically use like simple classification, and it can be used for simple classification regression problems. And the second category of machine learning, you have unsupervised learning, where machine understands the data and it identifies the pattern or the structure. And the evaluation is mostly like qualitative here. It does not do any sort of prediction or find anything specific in terms of unsupervised learning. The last category is like reinforcement learning. So here we use a reward-based learning, where your goal is to maximize the reward, right? Based on either a positive or negative reinforcement. The machine learns to act in a certain environment to maximize the reward. So in this particular presentation, all the application that I'll talk about is mainly focused on the supervised learning. And we'll show some simple benchmarks where how the photonics machines can be used for benchmarking this supervised learning techniques. So just to give a little bit of overview of the artificial neural network, we have ANN is basically a multi-layered, fully connected neural network, like the one what I'm showing here in this figure. They can mainly consist of an input layer, and then input data layer, and then you have the input node. There are like bunch of internal nodes which are like hidden nodes. They're all like connected, and then you have output layer, which is used for the output side. So given a node, it takes the weighted sum from its previous inputs, right? And then it passes it through some nonlinear activation function to generate some output. So in this particular neural network, the signal flows from left to right, and final outcome is calculated by performing certain procedure on all these nodes. So here is the simple schematics of a feed-forward network, which I'm showing here in the left of the top left of the slide. So the data is fed into the network in parallel. So you have this huge data that is flowing in parallel, right? And it passes through different layers. The input layer is shown in the green. It has certain weights, and these weights are the one which decide how the inputs are going to be mixed. And you have the hidden layer, which are shown in the blue, and then finally the output layer, which is shown in the orange color, right? So the results can be either a vector or it can be a simple one single output, right? So the output, if you take one of these node, you can actually look at the update rule. So you have this equation where you have the output activation function, which is nothing but it's basically a summed weighted input along with some bias value, and then you apply a nonlinear function on it or activation function. So that's a single neural node. And then in terms of inference is nothing but it's how this network kind of reaches decisions. And usually the calculation happens layer by layer basis, right? So the equation, this is just for one node, but we can also look at how if we take any one of this layer, we can actually convert this whole equation into a simple matrix operations by this particular representation. And if you try to expand it, starting from the output layer all the way to input layer, you get a recursive function here. So when you say training a neural network, we're talking about finding the weight which kind of minimizes the error of the actual one with the targeted, what you measure versus whatever is the targeted output, right? So usually, like the way the process works in case of training is you have this data which flows from left to right, and then you perform some prediction, and you have this true value. You generate the loss function, and then you propagate it. Like if you look at the overall thing, you have for each layer, you calculate the error from the targeted output using this loss function, and the derivative of the loss function with respect to weight is what is used for updating the weight rule. So if you look at the back, and one of the common algorithm that's used is called as backpropagation algorithm, where you find the weight that kind of minimizes the error of the predicted output with the true value, and then you apply the loss function. Then you have an optimizer which is used for updating the weight using certain rules. So here we can use say backpropagation algorithm, where you flow the data from left to right, and then you propagate the error back into the network, and then you keep repeating this or iterating it until you kind of settle on a weight which is converging, or you kind of happy with the error which is kind of minimal, right? So one of the problems with this approach is it's kind of slow because it's an iterative approach. And second thing is finding the local minima is kind of sensitive to whatever is the initial conditions, and it also depends on what activation function you use. Another thing is it can get stuck in certain local minima, or even it can, because of the gradients what you calculate, it can also become exploding gradient problems. So the approach what I've shown previously is just an algorithm. So you can implement either in the software, or you can have it very explicitly implemented in the ASIC chips. So here I'm showing IBM True North architecture, or the blocks, how it looks like. So if you look at this particular block, you have so many 64 by 64 neurosynaptic grid, core grids. And if you look at each core, you basically have router, and then you have certain scheduler and so on. But if you look at this block, most of the space is going to core SRAM, right? So what it says is like, even if you take any other architecture, a lot of time is spent in just reading and writing into the RAM. And that's a big bottleneck. And like it's almost close to 40% of the time it's just reading and writing into the RAM. And that's like a lot of wastage in terms of computing time as well as energy. So now if you look at so one of the interests that I'm having is like, okay, I want to very specifically focus on a time series problem, and for that we're talking about recurrent neural networks. So this is how the recurrent neural network look like. It's mainly used for solving temporal problems where you have some sort of temporal dynamics and the pattern is in the time, right? And you want to extract those patterns. The way it is done today for the recurring neural networks, like there are a lot of options there, like you have LSTMs and few other things, is you basically resort to certain back propagation through time algorithms where you're training the entire network, recurrent neural network. And this is kind of extremely slow, and it has the same problem which I discussed before. And sometimes you have to use a global optimizers like generic algorithm, and that can be very slow. If you look at where the reservoir works, the reservoir is like, think of it more like a approach where you are using some sort of indirect means to do computation. Like you have a bucket of water, and when you drop a pebble into the water, it generates some sort of ripple. And based on the ripple, what you see on the water, you can infer where the pebble landed, as well as what velocity it might have landed, as well as what could be the size of the pebble. You're doing a lot of indirect inference. So it's kind of analogic to that. Reservoir is something similar. You disturb the reservoir by using some sort of stimuli, and that disturbance kind of create some sort of transients, and the transient will be used for doing the calculations. So the reservoir it can be anything. So how do we train this reservoir? So we don't train the reservoir itself. The only thing that we train is the output layer of the reservoir. And we can use either like ridge regression, where you calculate the output based on this equation. And then you basically simple, like, prediction is nothing but whatever is the weight that you calculated times whatever is the test input that you provide. So now the next question is like, okay, so what would be what is the training approach like in terms of difference, right? So in case of artificial neural network, you basically have feed-forward network where the data flows from input to output, and then you propagate the error back into the network, right? And then you keep iterating until you converge on some sort of weight. And once you have the weight, you basically can run the system on the finally trained weight, and you get output, whatever is the prediction that you are interested in. In case of reservoir, what you do is you run the system, get the transient response, calculate the weight using a linear regression, and or even it need not be really linear regression, it can be some additional neural network, right? And then you basically can apply the estimated weight to get the system output. So it's kind of one pass. You don't go through iterative procedure here. So the question is then what can be a good reservoir, right? Because it's just a black box. And I would say like pretty much anything that you can think of which satisfy few basic rules. And that's going to be like it needs to have some sort of like basically pretty much what you find in the nature you can use it for as a reservoir, as long as it can satisfy a few basic requirements, right? You need to have some sort of nonlinearity as well as some sort of fading memory. So these are the two critical things, and you'll be able to express, and it can have some sort of fading memory property. And with this, you can do computing. There are a lot of materials in nature which can be used for computing for that reason. In terms of physical system that we have developed, what you find in the industry, you have like physical system based on MEMS, which are used as a reservoir. You have memristor based reservoir. There are like certain reservoir which are built on FPGAs, spintronics, photonics, superconducting. Out of all this system, photonics is kind of very interesting because it has this huge bandwidth all the way from few hertz to several hundreds of gigahertz. That's a huge bandwidth. Even if we consider like superconducting, its bandwidth starts from much higher gigahertz, so it cannot be applied on low frequencies. And you have other advantage with photonics, like you have the speed, where you can get the computing speed based on just the speed of light. And you have like inherent parallelism because you can use multiple wavelength and do like frequency division multiplexing and perform multiple tasks in parallel. It's very energy efficient because you don't have any dissipations because of any sort of charge carriers. And it's very robust to radiations. Um, and it can be easily integrated to our existing telecom networks. So that's where another advantage is. And then you get like with the material that we have in QCI, which is TFLN, we get like non-linearity, which is like chi-square non-linearity. And that kind of is one of the building blocks for machine learning. So there are few applications that you can think of where you can apply this particular machine learning or reservoir computing to any sort of real world problem which is time series based, we can apply it. And there are like plenty of things where it is time series, like your physiological signals, your ECG or EKG or few other physiological signals. They're all time series based. And we have been working with one of the universities where we have used the reservoir for doing brain signal analysis. And we are looking at how we can apply the reservoir for finding out like, anybody with epilepsy or even detect early symptoms of Alzheimer's. So we are looking at some of those research. Um, Economics is something which can be used, but I would not say that we can apply directly on the stock market because stock market is kind of chaotic, but there are other places where you will be able to apply it. Sensor fusion is another application where you can look at speech recognition. There are like some benchmarks that we perform where we shown that we can do the speech recognitions. We can apply it automobile industry where you do predictive analytics, and it can also be used for certain robot motion controls. So in terms of the architecture, we in QCI, like, we follow this delay feedback reservoir scheme. And the approach here is kind of simple. There are three layers. You have the input layer, you have the reservoir layer, and then there's an output layer. So in the input layer, the reservoir computing system, the input data is like streamed using the time division multiplexing scheme, and we use a mask or a random uniform matrix to convert or transform this k features what we have into to couple into the n nodes that we have in the reservoir. And the reservoir layer is not, it's more like a virtual layer. It's not real because we don't have a real nodes here. It's basically a slot that we assign in the time in the fiber, and that slot becomes a virtual node, and we can use that for performing computation. So it's a virtual node connected and it's coupled to each other using some sort of weight, and that weight can be implemented in multiple ways. So we use some sort of filtering techniques, which can also be used for like coupling these virtual nodes. So, sorry. So you have, as you can see here, there is only one nonlinear node. And that kind of is the case today because we are using like this is a starting architecture where you can build a simple reservoir using one nonlinear node, and then you can use some sort of delay which can be implemented using fibers, and then you have some sort of feedback gain which can be implemented either optically or electrically. And what we do is like we capture the transient responses that comes out from the reservoir, and we can apply we train once we have this transient responses captured, we can use this as the transformed output, train against whatever the expected output, and then we can get the output weights. So we can perform tasks such as classifications, or it can be even like prediction tasks as well as function fitting tasks. These are the three tasks that we can mainly use this for. So here I'm showing a simple animation of how the transformation happens. So what we do is like you have the single input U0 and we apply this mask layer which transform this U0 or U1 into, say, in this case, there are like 5 virtual nodes, 1, 2, 3, 4, 5, right? So you transform into this 5 nodes or 5 connected, 5 transform data, which can be like, serially fed into this reservoir and that kind of couples into this virtual nodes. And these nodes are not stationary. They're kind of like moving in the fiber. You can think of it more like laser light that is traveling in the fiber. So it kind of like moves from all the way from the nonlinear node back into the system. That forms a feedback loop, right? And then we capture these samples, which are nothing but, in this case, we capture the 5 virtual node values, and then we keep like, letting it circulate within the nodes, and that's how the memory is formed. And in this case, the nonlinear node, what we use typically in the optical layer is a simple Mach-Zehnder interferometer. And that kind of transforms the input to a nonlinear way. In terms of the products that we have, the first product which we uh, offer is EmuCore. So this was the first reservoir computing product that we built. It's more like an edge device. That is a photonic-inspired, not really a photonics device, but it's more like an emulation of a photonic-inspired architecture in FPGA. And the reason why we did this is to understand the market as well as have an easy access to anybody who wants to try the reservoir computing. And the architecture is very similar. You have a feedback loop, as you can see here. You have the programmable delay, which kind of acts like a fiber delay. And then you have the gain, which are the feedback gain. And then there are a few other parameters which kind of defines this reservoir. And we have the data flowing into this device through the Ethernet. And we can transform the data from any sort of like lower dimensional data into high dimensional data. It's more like a transformer. Um, These are some of the results that we have. So we did some benchmarking with the Norma 10. So Norma 10 is basically it's a moving average kind of regression where you have this very, very chaotic function defined by past 10 outputs as well as kind of multiplication of the past 10 inputs. It makes it like extremely chaotic. And as you can see here, it's kind of, you see, it's kind of fluctuates a lot, right? And the way we do this is like this inputs, what you see here, this is nothing but a random input. And we kind of generate a random number. Like if you want 2000 sample, we generate 2000 random inputs and we feed it into this function to generate this y of k plus 1. And that is also kind of random and chaotic. So this function is kind of random input chaotic function. And that's what you see here. What you see in this particular graph is you have this ground truth, which are based on feeding this random input to this function, and then you get this y of k plus 1. And then you have the reservoir where we feed the same random input, and it is kind of fitting the same function using the reservoir system that we have. And as you can see here, there is kind of extremely low error that we have both in the training as well as in the testing, except for a small area where there has been a big jump. So the first example that I shown with Norma 10, that's the function fitting problem. And most of the machine learning problem that you come across is a function fitting problem where you're trying to fit some input to an output. The only difference over there in the previous case is this is a function fitting in time where you have the past 10 input as well. So you're trying to fit it in terms of time temporal pattern. The second benchmark is trying to figure out the prediction, like you're trying to predict what the future outcome is. And here we use the Mackey-Glass delay ordinary differential equation. We perform the training using one-step prediction. And then we fitted the function using the reservoir, and then we try to predict what the next step is going to be. And here as well, it did a pretty good job in fitting this function. One other benchmark is MNIST handwritten recognition problem. This is not really a time series problem, but what we wanted to show here is that even for an image, we can actually serialize the data, and that becomes a time series problem. You can flatten the data, and you can think of it more like a scanner where you're trying to scan one line at a time, and then you can actually like figure out what the image is. So even with this, we got some pretty good results. In terms of other benchmark, we did some power measurements, as well as how much is the training time and inference time comparing against various other devices, as well as models. So we found like because we are talking about edge devices, so we compared with NVIDIA Jetson, as well as like there are some other benchmark with Apple M2, but this may not be the right thing to compare it against. But if you look at the Jetson, we are kind of competitive and also very close to what we have um, coming out from the EmuCore device, what we have. And the other benchmark, what we looked at is power numbers. We are at this point of time not having the best of the power numbers, and the reason for that is we didn't optimize the hardware, what you call the power domains or power management system in the software. But we have like fixed power of 6.4 watts versus like if you take Jetson, it's like 4.5 watt with the loading condition. And upon further investigation, we found that we can optimize this power projection all the way to 2 watts in the next iteration. Like there are like certain hardware optimization we can do to bring it down to 2 watt, and we can do the same kind of task what the Jetson has. So we are very power efficient when we do that. So the next iteration of the reservoir computing that we have, which is in the pipeline for the coming quarter, is NeuraWave. This particular technology is a PCIe 3.0 form factor, more like a GPU form factor system that implements an electro-optic reservoir computing system. It leverages like FPGA mainly for communicating with the host device, and it converts the digital data. It transmits the digital data into a high-speed ADC DAC, which is sampling at 1.25 gigasamples per second. And the main purpose of the FPGA is just to do a conversion from like just act as the interface to this high-speed ADC DAC. And there are very very small like functions such as monitoring as well as controlling some of the feedback gains. The core computation in this particular system occurs in the electro-optic feedback loop, and that's where the advantage comes from, where we can get like very high speed computation in the fly, and at extremely like at a reasonably power consumption. Like we need to take the power versus the performance, and we have total power consumption at this point of time around 36 watt max, and the dimensions is like something which is similar to one of the NVIDIA GPU, and also it's less than 2 kgs in weight. The prototype of this system is going to be available starting from Q4 2025. Plus, this takes like 3 slots at this point of time. That's similar to our GPU. And the future of future of what is the future of the reservoir computing, right? So I would say like it's all about making it smaller and also more power efficient. And the vision here is to make some devices which is going to be extremely fast, running at several giga giga samples per second, like 25 giga samples per second, and outperform the electronics. So that's the vision. And I believe when you move most of this computation into photonics, that's where the advantage will come in. Right now, it's kind of mixed architecture or hybrid architecture, but when you move fully into photonics, we'll have the advantage. And right now in QCI, we are moving towards that goal where we are making chips in our foundry to achieve some of these objectives. And the way we plan to do this is like have some of these photodetectors implemented in the photonic chips, laser integrated into the chips, and we'll have like bunch of like cavities as well as multiple reservoir cavities connected to each other. And that's pretty much all that I had for today.
No, thank you so much, Prajnesh. It really is incredible progress from QCI in what is a technically really challenging area. So now it's time to address questions from the audience. So just to remind everybody, at the bottom of your page, there's a Q&A facility where you can just submit your own questions and we'll address them. I'll put them to Prajnesh. So Prajnesh, can you tell me a little bit more about the contents of the EmuCore box that you've got as a product at the moment, and how the new PCI version, the prototype, differs from that inside.
Yeah, that's a very good question. So if you go back to the EmuCore, right, as I mentioned here, so all this block, what you see here, these are all implemented within the FPGA. So it's like emulation platform where you're emulating the photonics inside a FPGA, where you have this EOM, which is implemented like a lookup table, and there are like gains and delay, which is like also like not really a optical delay. It's like a FPGA delay. So all those things are implemented in FPGA, and interface here is Ethernet. And the key difference here is that Ethernet is has an upper limit, like you can't go very fast. It's limited either if you're using optical or like wired Ethernet, and that defines like how fast you can go. One is that, and the second thing is it's not having deterministic latencies, right? And when you go to the PCIe device, what happens is we are using a PCIe 3.0 interface right now, and that gives a throughput something closer to 4 gigabytes per second. And the system itself operates at 2.5 gigabytes per second based on the sampling rate of ADC and DAC. So we are like having that buffer to make sure that we don't lose any data. And that kind of gives somewhere around roughly 1,000 times speed up, 100 times speed up compared to what we have in EmuCore.
Great. And you mentioned towards the end that you're finally taking this down onto a thin film lithium niobate foundry platform that QCI have opened over in Tempe, Arizona. So
Yes.
we heard a lot about this in your first tutorial in May. And TFLN is what facilitates the electro-optic reservoir computing system on a chip. But
Yes.
can you elaborate a little bit more on how that system will look? How will it be packaged? You mentioned.
Sure. Yes. So the plan here is think of it like we can like whatever we have in here is basically one. This is like a one simple reservoir, right? So we can when we go to the chip, we can have like multiple of these reservoirs, and they can have different delays tau, and they can have different coupling between the reservoirs. So we can increase the dynamics between this and we can extract more patterns from this chip. And second thing is the speed of operation is going to be moving towards more higher throughput, because as you go smaller, the speed will increase.
Okay, great. And there's a few questions going through. So Harold Kimmy's asking if you're to purchase an EmuCore for proof of concept testing, do you have a suite of current examples or code that you could initially use for testing before running their own examples? And then leading on
Yes.
from that is, what is the largest data set you're using?
That's a good question. So far, like we have, so there are like a lot of examples that are available in our website, and most of these examples are more like I would not say like it has a huge data set where we run big amount of data set, but there's nothing limiting running a bigger data set. The biggest data set I have run is something to do with the voice recognition, where you have this huge number of samples from voice samples, and that can be we are tested. We have shown that yes, even with that huge data set, we can actually detect with a very high precision. Yeah, there are like a lot of examples that are available in the QCA website that can be used for first like experimenting.
Great, and Anel makes a great comment in the chat that speed is always limited by how fast you can get data in and out of the photonic chip.
Yes.
How are you solving that problem?
It's a great question. So we can go up to certain point. Let's say that we can go using a DAC. Let's say that we can go up to 6 gig, 10 gig, 25 gig, right? But then electronic is going to be the bottleneck. And not just that, even if you're sampling, ADC is going to be the bottleneck. So this is something that we are actively thinking about how we can go faster in terms of sampling the data as well as like how we can create the data, right? One of the approach we have been internally discussing is why not go the photonics route to convert the digital data directly into analog or optical. So we convert digital to optical. So that's something that we are actively looking into. And that is one of our approach where we can go faster. Second approach is like sampling at the output layer. There are many approaches where we can do the computation directly in the readout layer or output layer. And what we found is this sample data point that we are interested in or the results that we're interested in, they typically fall into the lower bandwidth domain. So you don't really need a very high speed ADC to sample this data.
Great. And you noted on one slide similar idle versus load power on the EmuCore.
Yes.
And you mentioned a path to, I think it was 2 watts, projected power of 2 watts.
Yes.
Can you at this stage share any more on the specific changes you need to make to get to 2 watts there?
That's a good question. So this was the initial prototype that we made, and so the path for bringing down the power to a lower wattage is something to do with the power delivery we have in the current system, where we have to change the power delivery circuits, and that's going to bring down the power consumption to a lower power wattage, and
Right.
also like some power management, enabling certain power management feature which is not enabled right.
Fantastic. And there's more questions. So in Anil mentions in his experience, a lot of heavy lifting is done by the ridge regression. Do you have any estimates on how much work is actually being done by the photonic reservoir?
Yeah, so that's a good question. I don't have the number at this point of time. So it depends on the problem size, what we're talking about. But it's most of the time, like, the iterative process, if you take a regular iterative process, that takes much more time and much more computing compared to ridge regression, which is more linear in nature. And one of the ways to address even like ridge regression, one of the ways to address this is like there is something called as online training, where you can move this logic into the FPGA, where the FPGA is continuously updating the weight and it's learning on the fly. So that's going to be much more efficient in terms of computation.
Great. You mentioned Andrea mentions in the chat that you mentioned integrated photodiodes and lasers.
Yes,
Presumably you mean this is hybrid integration with your thin film lithium niobate platform.
that's correct. It's going to be heterogeneous integration.
Yeah, yeah, yes. Great. And so where is the crossover point versus GPUs, TPUs, in terms of data set size, latency budget, or power envelope, where you say reservoir actually wins by design?
Yes. So it depends on what is the market that we are talking about. Like this particular system that we are talking about, we want to go for energy efficient system. So that means that it's not necessary that we need to develop something where we can learn an LLM, but it can be as simple as a very small model, which might require very, very high speed. but we might be more focused on the efficiency. It may be something that runs on the edge, right? So that's where the differentiation happens. That's why I was like talking about edge devices.
And there's another question in the Q&A from Jorge Monroy Ruz. Could you share if phase noise, like the one that can be introduced with optical fiber delays, is a problem for this type of reservoir scheme?
So, so what kind of phase noise is the question? I didn't understand the question here.
Okay, no problem. Maybe Jorge, if you can write in the Q&A what type of phase noise you mean. So, if I can maybe go on to, how do people get their hands on this prototype device, the next PCI card?
So we have a very limited quantity at this point of time. Like, what we manufacture at the low run production volumes. And once we start like, distributing for the first initial, more like a pilot run or the initial, what do you call, like initial customers, that's when like it's going to be opened up for mass. Like we start doing the mass production, and that's how we'll open it up for rest of the customers. But it should be something that's going to be available in the website for pre-orders.
Great. And in terms of system integration, what does the software stack look like? What do you
Yes,
supply with it?
that's a good question. So this is a standard PCIe device, at least for the NeuraWave. And the interface is going to be like you just like take any desktop system, plug it in, and then you'll have the system should automatically detect it by the host machine, and the drivers will supply the drivers. You load the drivers, and that is going to be a library which will interface to this device, and it will expose via the Python layer. And then you can directly like call the you can make some of the calls which are like in the Python layer to communicate with this device or the PCIe. So most of the development will be at a low level. The native libraries are going to be written in C program, and the programming interface part of it is going to be at Python layer.
And going back to the actual chip, do you plan to integrate it with a dedicated EIC?
Sorry, can you repeat the last part of it? I didn't follow it.
Do you plan to integrate the photonic chip with a dedicated EIC as well?
I6, you mean?
Yes, yeah.
Yes. So, so that's something. So the approach would be like, first we do the TFLN chips and do the initial testing using, say, FPGA. Like, we might have certain bigger FPGA chips sitting in a different test board, test it out. And once we have the logics and everything, written in FPGA, that can be transferred into an RTL, definitely something that we'll be looking at.
Thanks, Prajnesh. So I think we've addressed a lot of the questions in the Q&A. So I guess I'll leave you with some key points that I kind of took from this is that reservoir computing is very fast to train and hardware friendly. And QCI's EmuCore system shows very promising results with power headroom as well. And the PCI electro-optic card plus future shrinkage to photonic chips using the TFLN platform is really strong and impressive trajectory. So my call to all of you watching is to reach out to QCI if you want to exploit their pilot or demo. And on behalf of Optica, our speaker, Dr. Prajnesh Vijay Kumar, and all at QCI, thank you so much for attending and for your attention and your questions. Please keep us updated with what you build when you get your hands on one. We'd be very interested to find out. So we'll get together with QCI again on October the 30th for another industry tutorial. Same time, same platform, so look out for that. But thank you all, and bye for now. Thank you, Prajnesh.
Thanks, John. Thanks, everybody. Bye.